have my cord here in case I start to run out of, the battery goes down, because I've been kind of pushing that right now. That's the least of our worries. Okay, so another type of classic calculation that combines the two things that we've talked about so far. We talked about solution concentration, specifically molarity. So we're going to talk about molarity here. And we also talked about stoichiometric calculations. So we're going to combine those two into what's called, what does aqueous mean? Water is the solvent, yes. So as water the solvent, we're going to deal with the molarity of solutions, and we're going to talk about using a balanced chemical equation. We're going to talk about amounts between reactants. That's exactly it. This is that very busy slide I showed you, so we'll take a look at it again. Of course, we've been saying if you have the balanced, BAL for balanced equation, okay, you can go back and forth between moles of reactant or product, or product or product, or reactant, reactant, using a stoichiometric ratio. We said that usually stoichiometric calculations, you're going from the mass of something to the mass of something else, using the molar mass to stoichiometric ratio, molar mass, back like that. We talked earlier, if it's a pure substance and you know the density of that pure substance, you can go from volume, use density to get mass. And here we have mass, use density to get volume. Down here, we talked about we can use Avogadro's number to go between moles and counted particles. Okay. Then most recently, if you have the molarity of a solution, if you have the molarity of a solution, you can go back and forth between moles and volume. And actually this right here, I know that's just very busy, but this is actually what we're going to talk about right now. The aqueous solution stoichiometry problems. So the chemistry, there's all sorts of kind of slants on the problems that you might run into. These, generally speaking, are the two things you're after. One of these two things. You're either after concentration, I'll go ahead and say concentration in terms of molarity, or you're after volume. One of those two things of a reactant or product. So in algebra, you probably know that if you have one equation, you can have one equation and one unknown, and you can solve for that unknown. So that's exactly what we have. So we have these three variables: molarity, molarity is a ratio of moles to volume. And if you know two, if only one thing is unknown, if you know two of those quantities, molarity, moles, or volume, you can get to the last one. That's it, just by rearranging. Okay. So aqueous solutions, stoichiometric calculations go something like this. And I really like to kind of do what I did with the other stoichiometric calculations. I like to write underneath the balanced equation what we have. So here's the question at hand. It says, what volume of 0.235 molar NaOH? So I find my NaOH, I write question mark volume, I go ahead and write 0.235 M under my NaOH. Now, on your unit exam in here, you're going to have an aqueous solution stoichiometric calculation. Take the words, unpack the words, put them under the balanced equation, and see what you got. It goes on to say, is needed to react with, then I have a volume, 35.0 milliliters, and I have a molarity, 0.108 molar, that's associated with the other reactant. So I'm going to go ahead and put that under my H2SO4. 35.0 milliliters and 0.108 molar. So to work a problem like this, I always tell students you start with the thing you know most about. Well, I definitely know, the only question mark I have is with regard to the NaOH. And just like I said a minute ago, if you know two of the three quantities, you can get to the third. So in this case, is that somebody's phone in here? That is so cute. I hope it's buzzing. No, but is it? I was like, oh, that is so like.
Oh, it's dead. I had
20,000-ish.
Yeah. Okay.
That's good. they're trying to build more classrooms that have access for students to keep their electronics charged. But, so if we have volume and molarity, we can get to moles. Probably good with that. So actually, I'm going to put the step number 1, down under here, under the H2SO4. I'm going to get to moles H2SO4. Step number 2, a different calculation. I'm going to break them up with little headings. Once I have moles of H2SO4, I can get to moles of NaOH using the stoichiometry of 1 to 2. That makes sense? Just like we talked about. And then once I have moles of NaOH, I can use moles of NaOH and molarity to get to volume. I'll go ahead and, to get to volume, I'll go ahead and put a little 3 up there. That's kind of a roadmap of how we're going to do this. We start with what we know most about, which is the H2SO4, go then to the moles of the other thing, use moles and molarity to get to volume. So it looks like this. So I kind of told you before when we were doing problems with solutions, like dilution problems and all that, I'm really a firm believer, I used it in my slides on blue. The blue is my header. The cool thing about a header like this is notice that I say in the header, and I wouldn't write this, I just say moles of H2SO4. I probably wouldn't do all that stuff. But if in my header I say what species I'm working with, H2SO4, I don't have to explicitly label anything. So underneath the H2SO4, of course, we had 35.0 milliliters. We're going to use the moles per liter here in a minute, but we have to get this to liters, right? And you guys would tell me I need to go ahead and put 1 liter of solution over 1,000 milliliters of solution. Now I'm going to use what? The non-flipped version of molarity to get to moles. So under the H2SO4, I had that 0.108 M. And that meant 0.108 moles of H2SO4 per 1 liter of solution. So now units of milliliters cancel, units of liters cancel, and we're left with units of moles of H2SO4, which is my goal here. Now, if you choose not to break a problem like this up into steps like I'm doing, you have to be explicit with regard to the species you're talking about. This class, I'm emphasizing communication. Even if you get the right answer in the end, but you have milliliters, moles, liters, you don't explicitly tell me what you're doing, even if you get the right answer, it's not right. All right, so how many sig figs? I'm liking 3, very good. Okay, so 3 sig figs looks like this. Cool. So now I'm going to kind of piggyback on that in my next thing. My next little part to this working this problem. So now I'm going to leap from the H2SO4 to the NaOH using the stoichiometric ratio. So my first term is going to be that 0.00378 moles of H2SO4. Now I do have to be explicit because in my ratio it's going to have moles of H2SO4 what? In the bottom, right? And moles of NaOH in the top. What number will go in front of the moles of NaOH? 2. Yep. So I put 2 moles of NaOH from stoichiometric coefficients, 2 over 1 mole of H2SO4. 3 sig figs again. Okay. So I got 0.00756 units then would be moles of NaOH. And I don't usually do this on my answer key, but if you wanted to take a number like this and go ahead and repost it up under your NaOH, you could. So NaOH, under NaOH, we had question mark volume, we had the molarity, and now we have moles. So we're going to use the moles and molarity we knew to get to the volume. So my last step to get to volume, I'm going to take this, and that's going to be my first term. So 0.00756 moles of NaOH over 1. If I want units of moles of NaOH to cancel, what will the units in the denominator of the next term be? Moles of NaOH. So what? This is the flipped version of the molarity, isn't it? So 1 liter of solution over 0.235 moles of NaOH. I'm telling you, and I feel like you're a parent at this point, but the more you can stay organized and you have a balanced equation that you're doing this problem with, the more you're not going to mess up and put the wrong molarity. Right? How many sig figs? 3. Very good. Now, sometimes, and I can't remember what my slides do here, but sometimes we want volume in milliliters instead of liters. But to me, I don't think it asked for it. But you see, I went ahead and tacked on, to get it from 2 milliliters, I put 1,000 milliliters on the top and 1,000 milliliters solution on top, 1 liter solution on the bottom. You told me 3 sig figs, so I got a cute little 32.3 milliliters of solution. Now again, notice that I'm not very explicit. Which solution is that? Well, it's my NaOH. How do I know that? Well, I labeled my calculation. Okay, so to me, if you do the little blue headers, you're like, it helps who's looking at your work, it helps you stay organized, and you don't have to be as explicit. So let's work another one kind of like that. Here's another one, so I'm going to go ahead and go word for word, and I'm going to take out the information and write it under the balanced equation. So it's the same chemistry, right? Things have changed up a little bit. So in this case, what is the concentration? And I'll go ahead and make it the second slot under my H2SO4. So I'll put question mark M. What is the concentration? It doesn't say it, but we're after molarity of H2SO4. Now it goes on and says, if 25.0 milliliters of the solution. This is the way these things read. What do you think that volume is associated with what species? How many people think it's associated with the NaOH? How many people think it's associated with H2SO4? Yeah, interesting. It is associated with the H2SO4. What is the concentration of an H2SO4 solution if 25.0 milliliters? It doesn't say of that solution, but it's instead of that, it's that solution. Yep, it is with the H2SO4. So I'm going to put 27.7 milliliters. And if you're like me, a lot of times if I'm faced with a new chemistry problem, I have to read several times. And you probably would have caught which one it is. If you read on 25.0 milliliters of the solution required 27.7 milliliters of 0.444 molar NaOH. So to me, you read this, you're like, okay, well, I think this volume, 27.7 milliliters, and I know that molarity goes with my NaOH. So I'm going to tuck them away underneath my NaOH. So I'm going to go, oh, darn it, are you serious? What did I do here? Sorry, guys, 25.0 milliliters, final answer. This goes with this. That's what I was trying to emphasize. The second volume and second molarity go with my NaOH. 27.7 milliliters and 0.444 molar. So what do I know more about H2SO4 or NaOH? The NaOH. I know more about it. My first step is going to be go ahead and use volume and molarity to get to moles of NaOH. Then I'm going to use stoichiometry to get to moles of H2SO4. And then I'm going to use my moles and my volume to get to molarity. That's it. So that's my third thing over here. And again, I'm going to see these blue titles to label these things. So the first one's going to be labeled moles of NaOH. I probably would just say moles of NaOH. I probably wouldn't do this whole thing. Moles of NaOH, I start with the volume, 27.7 milliliters over 1. I'm going to use the molarity that I have for NaOH, but that's moles per liter. So I have to get this milliliters to liters. So it looks like this, 1 liter of solution over 1,000 milliliters of solution. Now I want liters to cancel, be left with moles, so I'm going to use the non-cooked version of the molarity of NaOH, which is that 0.444. So 0.444 molar means 0.444 moles of NaOH over 1 liter of solution. Milliliters solution cancel, liters of solution cancel, units of moles of NaOH, which is perfect. 3 sig figs again, right? So I got 0.0123 moles of NaOH. So I kind of filled out that column for my NaOH was my second of 2 reactants. So now we're going to go from moles of NaOH to moles of H2SO4. I'm going to piggyback on this, my first term in the next part of the calculations, that 0.0123 moles of NaOH, usually over 1. So you guys would tell me if I want moles of NaOH in the first term to cancel with moles of NaOH in the second term, I have to put units of moles of NaOH in the denominator. And I'm going to put 2 moles of NaOH in the denominator, 1 mole of H2SO4 in the numerator. So half of 0.123, 0.013. Now we talked about this before with stoichiometric calculations, and these guys right here bring no uncertainty. Those are exact. So yeah, we have 3 sig figs again. It's kind of our MO today. So rounding it to 3 sig figs, I got 0.00615 moles of H2SO4. This might be one of those good examples where if you take a half of something that ends in an odd number, like 0.0123, you know that you have to have rounded up to get this last digit as it is. So sometimes if you use an unrounded number for your last part of your problem, you're going to get a slightly different answer, which is not your problem, but that's mine when I grade it. So rounding between steps is fine. So I'm going to use this as, so the last thing, if you look under H2SO4, now what do you have? You have a volume, which is that 25.0 milliliters, and now you have the moles, which is 0.00615. We're after molarity. Molarity is a ratio of moles to volume. So on the next one, all I'm going to do is take these moles, and I'm going to divide it by the volume I have for H2SO4. So we got 0.00615 moles of H2SO4 divided by the aliquot, 25.0 milliliters. Nice round volumes were probably gotten from pipettes. Now that won't give me molarity. What one last thing do we need to do? Yep, we need to multiply that by 1,000 milliliters over 1 liter. Perfect. 1,000 milliliters of solution over 1 liter of solution. Then we know molarity is units of moles per liter. We're in good shape. How many sig figs? 3 again. Yep. So you're looking at a solution. I think I talked about this the other day when we talked about solution concentration. I would just probably put 0.246 m and then what the solute is. 0.246 molar H2SO4. They're kind of fun. They're not bad. Like I said, I think it'd be right underneath the thing, what it is. So let's do another one and kind of change it up a little bit. Let's see why this is different. Now we're focusing on a product. As Na2SO4 is sodium sulfate. So it says, what is the concentration of Na2SO4? So question mark, I'll go ahead and put molarity as the first one. Question mark molarity. Okay. It goes ahead, and we're kind of piggybacking on the previous problem, where here a little bit ago we had 25.0 milliliters of H2SO4 at a molarity. Well, we figured out the molarity. The NaOH, we had the volume of 27.7 milliliters, and we were given in the original problem the molarity of the NaOH. And we did a problem where we came to the molarity of H2SO4. So, all right. Well, in this problem, here in a minute. We're going to start kind of like we did before. We can use volume and molarity to get to moles of NaOH, right? And actually, if you don't mind, I think I'm just going to go ahead and use that value we had a few slides ago. Then we can go from moles of NaOH to moles of Na2SO4. Now, if we had, and we do, if we had the volume, we could take the moles, like we did before, moles divided by volume, get molarity. The catch here is, what do you think by the time I get to the reactions over, what will this volume be? It's a product solution. Picture basically, how would this work? Picture you had this in a beaker, and then you added this, those are your two reactants, and then you formed these. So what would the volume of that solution be? And how did you get that? Yep. These two volumes added together is equal to the volume that your products are swimming around in. That's it. That's totally it. So let's do this problem. So like I said, if it's okay with you, I'm just snagging the 0.0123 moles of NaOH that we got from the molarity and the volume from the previous slide. But now my stoichiometric ratio is going to be different because I want moles of NaOH to cancel. I want to be left with moles of Na2SO4. So it looks like this, right? 1 mole of Na2SO4 over 2 moles of NaOH. Divide that out, give ourselves 3 sig figs. The moles of Na2SO4 produced must be that 0.00615 moles of Na2SO4, which coincidentally was the same moles of H2SO4, wasn't it? Which makes sense because they're present in a 1-to-1 ratio. Anyway, but we've done it mathematically. So then under my Na2SO4, now I have moles, and I just have to divide by the total solution volume. Which, don't forget to show all of your work. You have to show this addition. You're like, are you serious, Mrs. Snipes? Yes, Mrs. Snipes is serious. Don't make me nickel and dime you on a test. So the volume of our H2SO4 was 25.0 milliliters. The volume of our NaOH was 27.7 milliliters. Of course, we round up to decimals, so we get 1 decimal in both. So we have 1 decimal in our answer, 52.7 milliliters. So now I'm ready to go ahead and take the ratio of moles to volume here. So to finish this out, the molarity will look like this, that 0.00615 moles of Na2SO4 divided by the solution volume, like the product solution volume, 52.7 milliliters. And then you guys told me I can't stop there. I have to get in the denominator some milliliters, I get liters. So we're going to multiply by 1,000 milliliters of solution over 1 liter of solution. Rounding again to 3 sig figs, we can, our molarity of our Na2SO4 would be 0.117 molar, 0.117 molar Na2SO4. So physical science problems, including chemistry and physics and well, biology, science problems in general, you kind of have to kind of picture what's going on. In this case, we had to envision the volumes of the 2 reactants going to make the volume of the product. It's like a little story. All right. Well, in Thursday's lab, when we hear for your note, you guys are going to do this technique called a titration. And I have a little video, which I think we can show you now. It's going to show you how this works. But basically, you have your 2 reactants. You have your 1 reactant in what's called a burette, and you have when your one reactant kind of doused down here, you're dripping into. So when it talks about incremental amounts, it's talking about the burette dripping material in, okay? Now, the reason you drip it in is because basically what you want in your reaction flask is when you are done with your experiment, you want all of the 2 reactants to be entirely consumed, no leftovers. We've talked about something in excess, nothing in excess, both in limited supply amounts. It's just that sweet point where that's all used up by dripping that in. Okay, that's what we call the end close point. So this is the burette, and I'll try to remind you of this on Thursday, but in case I don't, you kind of see the whole parallel thing. This thing's called a stopcock over here, and this is parallel with the gizmo that holds your liquid. If it's parallel, it's totally open. If it's kind of like a gas jet. If it's perpendicular, it means it's totally closed. Anything between is a little bit open. Okay, so you'd be in good company if you go to fill it and you've got it like this. You're like, oh, stop it out. Okay. So yeah, I was not giving you guys the figure there. So there's a burette. Notice it has 2 spellings, just like pipette has 2 spellings. Like, are you serious? So I kind of mentioned here the 2 things going on here. This in the burette is called the titrant. Thus titrations, titrant. This here in the beaker is called the analyte. It's a beaker, but what works well actually are Erlenmeyer flasks because of the sloped beakers are Erlenmeyer flasks. So here we have a person. The one thing I don't like about this OpenStax video photo is that it has, if you look real closely, it looks like the titrant. I'll go ahead and put T for titrant. That's what's in the burette. To me, it looks like the titrant is the same color as the analyte. And usually they're not. I think they're just making blue. Okay, starts with the letter M. What do we kind of call this bottom of the kind of meniscus? Yep. So in lab on Thursday, you're going to have to read the bottom of the meniscus always. And we already talked about gradations. Remember clear back when you guys did lengths, you guys had to measure between the gradations. So the other thing about a burette that drives me nuts is it goes backwards. Like you see 0 at the top, and the ones we're going to use in lab have 50 milliliters at the bottom. And that's on purpose. Because you figure as you drip, it's going to go from 0 to 10, to 20, to 30, to 50 milliliters dispensed. Okay, so let's see. If I had to say what this is, each one of these, so there's a 1 milliliter, there's 2 milliliters, 3 milliliters, etc. So each, does this make sense? So that one is 0.5. So each of them is a tenth, so we have to measure between the tenths. So to me, it's not even to the 1, so I would go 0. Let's see, 0.1, 0.2, 0.3. I'd go 0.3, and to me, I have to kind of estimate between the 3 and the 4, and I'm going with 6, 0.36 milliliters. Now you might be kind of a little different in that last digit, but we should all agree on it not being any in the 1s and the 3 in the 10ths. Okay, so that's what I'm going to be looking for. So here's our little video. In a minute to do a calculation. But you kind of saw where that person, you saw the titrant and the analyte, okay? And you saw him kind of mix, him or her kind of mix it so that you could go ahead and get those 2 to mix to see if the pink actually is actually what you guys are going to do on Thursday, use on Thursday. It's called phenolphthalein. And you're going to, when the pink stays, that means you're at your end point. So, so here are some things that need to be in place in order for a titration approach to work. One is that you need to be able to dissolve your reactants in water or some sort of solution, some sort of solvent. The other is in order to finish up doing your calculations, you need to know how they react, molarity, stoichiometry-wise. The other one, this kind of gets to the person kind of jiggling it, it needs to be relatively fast. Because you can imagine if you drip in some of your titrant and it takes 5 minutes in order to react with your analyte, you know, that delay could it could really screw things up. So it needs to be pretty fast. The other thing is you need to count on it going to completion. We kind of talked about chemical equilibria or side reactions. And then you saw the pink color. I don't know, I've done a few of my fair share of titrations, I will admit, where I forgot to add the phenolphthalein, I forgot to add the indicator. And so here I have two clear liquids, and I titrate and titrate. Like, I know I passed the endpoint, and I just forgot to add indicator. So you need to be able to see where the equivalency point is. The indicator is a great one. The other one is potentiometrically kind of determining the endpoint. So I have two E's here. Okay, equivalency point and endpoint. Now, equivalency point is if you were to look at the particular molecules involved, the molecules of the two reactants, then the titrant being added to the analyte, the equivalence point is right at the point where all of your analyte is used up by titrant. That's it. Sometimes we call it the EP, equivalence point. Okay. The end point is when the investigator, that's you and me, whether it's turning pink or a potentiometric way, says, I know I am right I'm done. I know that all of my analyte has been used up by titrant. So ideally, they are the same, okay, and they both have the same abbreviations, right? Equivalence point and endpoint. But endpoint is what we'll catch it as. So I talked about how do you know that you have used up all of your analyte, and one is a colorimetric one, using an indicator, and the other is to look at its conductance, okay, potentiometrically. So we're going to now do a problem where we take the video stuff. Now, if I could have replayed the video, you would have seen the meniscus and you would have written down the initial volume, the initial burette volume, like what we had. We had 0.3, what did I do? 6, thank you. Yeah, that was our initial burette reading, but this is going to be different here. So we write initial burette reading, a final burette reading, and then we have to do a simple subtraction to get the volume dispensed. And then that's what's going to go under our titrant. So here we go. In this case, or what we just saw, the aliquot of analyte was 50 milliliters of acetic acid. I find acetic acid, write 50.00 milliliters under it. Okay. Then I find the molarity has to do with my NaOH. So I'm going to put, under my NaOH, I'm going to put 0.1150 molar. All right, I don't know anything about anything, right? So I'll put an A next to my 50 milliliters for acetic acid for the analyte. I'll put a T next underneath the sodium hydroxide to mean that's the titrant. That's the titrant is in the burette. So down here we see a couple of volumes for the burette, for the titrant in the burette. We have the initial 0.48 milliliters, and we have the final 23.90. Like I was saying a minute ago, all we have to do for the volume here for our NaOH is simply take the final, which is 23.90 milliliters, and from that subtract the initial 0.48 milliliters. It might be even a fair question. You might be saying, well, Mrs. Snipes, why start at 0.48 milliliters? Why not start at 0? Well, because there's uncertainty in every gradation marking. Like, Mrs. Snipes, I can get that meniscus right on 0. Well, in what you guys are going to do Thursday, your instructions are don't start on 0.00. So that's what we're going to do. And then to work this problem, doesn't it make sense? We can use that volume and molarity to get to moles. And then we can get to moles of this using stoichiometry. And then we can use the volume and molarity to get, to get to molarity. The volume and moles, to get to molarity. That's it. All right. So let's knock down our subtraction first. The volume of titrant, it's always going to be the final burette reading, which is 23.90 milliliters. And from that, subtract the initial burette reading, 0.48 milliliters. So the volume dispensed of our NaOH is 23.42 milliliters. Again, notice that I have my little blue heading there. You guys have plenty of time on your test. You should have plenty of time working your problems too. You should work problems like they're tests on your test. So here in a minute then, I'm going for the moles of NaOH using that volume and the molarity of NaOH. So here's the volume of NaOH, 23.42 milliliters of solution. I have to get that to liters using 1 liter of solution over 1,000 milliliters of solution. And then I want liters of solution to count, so I'll be left with moles. So I look up at my NaOH and I know its molarity was that 0.1150 molar. What that meant for the NaOH was 0.1150 moles of NaOH per 1 liter of solution. How many sig figs? Life got interesting. We get 4, yep. So your moles of NaOH are 0.002693 moles of NaOH. The next step kind of on our strategy was to get to the moles of is it HCl? So we're going to piggyback on that. Moles of CH3COOH, moles of acetic acid. So if we put now, our first term is that 0.002693 moles of NaOH over 1. This has the boring stoichiometry of 1 to 1, right? So then the next ratio simply goes 1 mole of CH3COOH over 1 mole of NaOH, which I can do that math. We get back 0.002693 moles of CH3COOH. And we're almost done. At this point, we've worked a few of these before, where now we have the moles, and if you look back, there was a 50 mil aliquot, right? So we're going to take, to get to molarity, we're going to take these moles, divide it by the volume, which was 50.00 milliliters. We have to, you guys would tell me, introduce 1,000 milliliters of solution over 1 liter of solution. And then finally that leaves with the units of molarity, which is moles over liters. You guys would tell me again 4 sig figs. And I get 0.05387 molar CH3COOH. Okay. Oh yeah. Any questions about that? So I can't remember how many there are. Like I said, as you guys are feeling the pain, know that this summer I was feeling the pain, and I've got Unit 3 problems done for this class. I still need to do Unit 4, not to mention you. So, anyway. Let me know if you have any questions.